Imagine you're standing outside during a heavy rainstorm. Raindrops are falling from clouds thousands of feet above your head, plummeting down toward you at what should be terrifying speeds. And yet, when they hit your skin, they just feel like tiny taps. A little annoying maybe, but definitely not dangerous. Now, here's the wild part. If those same drops of water were thrown at you by someone standing just 10 feet away at the speed they should be falling, they'd sting like crazy. So what's going on here? Why doesn't rain hurt us? Why don't raindrops punch holes through umbrellas or shatter windshields? The answer hiding in those innocent little drops reveals one of the most beautiful secrets of physics, and once you see it, you'll notice it everywhere. Let's start with a simple thought experiment. Imagine you drop a tennis ball from your hand. It falls to the ground pretty quick, right? Now imagine you drop that same tennis ball from the roof of a two-story house. It hits the ground faster and with more force. Makes sense. Now drop it from a 10-story building. Even faster. Drop it from an airplane. Faster still. So here's the natural question. If you keep going higher and higher, does the ball just keep going faster and faster forever? Could you drop something from so high up that it would hit the ground at 1,000 miles per hour? 10,000? What's stopping it? Your intuition might say yes, it should just keep accelerating. After all, gravity is pulling on it the whole way down. The higher you go, the longer gravity has to do its work. So the faster the object should be moving when it lands. And for a little while, that's exactly what happens. But then something fascinating kicks in. Something starts fighting back. And that something is the air itself. See, we think of air as nothing, as empty space we move through without resistance. But air is actually made of trillions and trillions of tiny molecules, mostly nitrogen and oxygen, all bouncing around like crazy. When you're sitting still, you don't notice them. But the moment you start moving through the air, those molecules push back. The faster you move, the harder they push. It's like walking through water. Move your hand slowly through a swimming pool and it's easy. Try to punch your hand through the water really fast and suddenly there's serious resistance. Air does the same thing, just way less dramatically, because air molecules are much more spread out than water molecules. So here's what happens to our falling tennis ball. At first, when you drop it, gravity is the only major player. It pulls the ball down and the ball accelerates, getting faster every moment. 1 meter per second, then 2, then 3. But as it speeds up, the air molecules start hitting the bottom of the ball more and more often and with more and more force. This creates what we call air resistance or drag. At low speeds, drag is tiny, barely noticeable. But here's the key. Drag grows dramatically as speed increases. In fact, it roughly grows with the square of the velocity. Double your speed and the air pushes back about 4 times harder. Triple your speed 9 times harder. You see where this is going. So we've got 2 forces now. Gravity pulling down, which stays constant, and air resistance pushing up, which gets stronger as the object falls faster. At first, gravity wins easily because drag is so weak. The ball accelerates. But as the ball gets faster, drag gets stronger and stronger and stronger. Eventually, something beautiful happens. The drag force pushing up becomes exactly equal to the gravitational force pulling down. When that happens, the forces balance perfectly. And when forces balance, acceleration stops. The ball stops getting faster. It's still falling, still moving downward, but now at a constant speed. We call this speed terminal velocity. Terminal velocity isn't some mystical speed limit built into the universe. It's just the speed where the forces balance. And here's what's really cool. Terminal velocity is different for every object depending on its weight, its size, and its shape. A feather has a very low terminal velocity because it's light and has a large surface area that catches a lot of air. It reaches force balance quickly, at just a few miles per hour. A bowling ball has a much higher terminal velocity because it's heavy and compact, cutting through air more easily. It might reach 100 miles per hour or more before drag catches up with gravity. Now let's come back to our raindrop. A typical raindrop is tiny, usually just a few millimeters across. It's not very heavy, maybe a fraction of a gram. And importantly, it's not perfectly streamlined. It's kind of round and squishy. All these factors mean that air resistance builds up pretty quickly as it falls. Scientists have measured this carefully, and it turns out that most raindrops reach terminal velocity at somewhere between 10 and 20 miles per hour. Some bigger drops might hit 25. That's about the speed of a casual bicycle ride. Fast enough to feel, but nowhere near fast enough to hurt you. But wait, you might be thinking, clouds are really high up. Some clouds are miles above the ground. Doesn't that give raindrops plenty of time to reach insane speeds? Here's the beautiful part. It doesn't matter. See, once an object hits terminal velocity, that's it. Game over. It cannot go faster no matter how much farther it falls. You could drop a raindrop from the edge of space, and after a few seconds it would hit terminal velocity and then just coast the rest of the way down at that same gentle speed. Height doesn't matter once terminal velocity is reached. What matters is the balance between weight and air resistance. Let me give you another way to think about it. Imagine you're in a car driving down the highway at 60 miles per hour. If you stick your hand out the window, you feel a strong force pushing your hand backward. That's air resistance. Now imagine you press the gas pedal to go faster. Your engine has to work harder and harder to overcome that increasing air resistance. Eventually, even with the pedal floored, your car reaches a maximum speed. That's basically the car's terminal velocity, the point where the engine's forward force equals the air resistance pushing back. Same idea as the falling raindrop, just horizontal instead of vertical.
Now here's where it gets even more interesting. Not all raindrops are the same size, and that matters a lot. Tiny droplets like the ones in mist or drizzle might be only 1/10 of a millimeter across. These little guys have a terminal velocity of just a couple miles per hour. They basically float down. That's why mist seems to hang in the air. On the other extreme, the biggest raindrops that can exist are about 5 or 6 millimeters across. Any bigger than that and they break apart as they fall because the air rushing past them tears them into smaller drops. These monster drops can reach terminal velocities around 25 miles per hour. Still not dangerous, but you definitely feel them hit. So the rain that falls on you during a storm is this whole range of drop sizes, each one traveling at its own personal terminal velocity determined by its size and weight. The result? A gentle pitter-patter instead of a deadly barrage. Nature, through the simple physics of air resistance, has given us a built-in safety system. Isn't that remarkable?
But let's push this further. What if there were no air? What if you could somehow remove all the atmosphere and drop a raindrop from a cloud? Well, now there's no air resistance at all, only gravity. And gravity would accelerate that drop the entire way down. From a cloud 5,000 feet up, by the time it reached the ground, it would be traveling over 300 miles per hour. At that speed, even a tiny drop of water would hit you like a bullet. It would be absolutely lethal. Every rainstorm would be a disaster. Life as we know it couldn't exist. We owe our comfortable existence during rainstorms entirely to the air we often take for granted.
You can see terminal velocity in action everywhere once you start looking for it. Ever notice how skydivers fall? When they first jump out of a plane, they accelerate for about 10 to 15 seconds until they reach terminal velocity, which for a human in a belly-down position is around 120 miles per hour. After that, they're not really falling anymore in the sense of accelerating. They're just flying through the air at a constant speed. The ground is rushing up, sure, but their velocity isn't changing. When they open their parachute, they suddenly increase their surface area dramatically. More surface area means more drag at the same speed. Now, the drag force is much bigger than their weight, so they decelerate rapidly until they reach a new, much lower terminal velocity of maybe 15 miles per hour, gentle enough to land safely. Or think about leaves falling from trees in autumn. They twist and tumble and drift slowly to the ground because their large, flat surface area gives them enormous drag relative to their weight. Their terminal velocity is so low they seem to float. But if you crumpled that same leaf into a tight ball, reducing its surface area, it would fall faster because now drag builds up more slowly. Here's another fun one. Cats. There's this famous, somewhat dark observation that cats who fall from medium heights, like 2 to 6 stories, often suffer worse injuries than cats who fall from greater heights. Why? It's terminal velocity again. A falling cat takes a moment to spread out its body, increasing surface area and drag. If it falls from a medium height, it's still accelerating when it hits the ground. But from higher up, it reaches terminal velocity, spreads out to slow down as much as possible, and actually hits the ground at a more survivable speed. Nature is full of these strange terminal velocity stories. Now, you might wonder, what about hail? Hailstones can definitely hurt. Some can even kill. How does that fit with our raindrop story? Well, hailstones are not raindrops. They're ice, which is denser and heavier than water. And they can be much larger, sometimes the size of golf balls or even baseballs in extreme storms. Bigger and heavier means higher terminal velocity. A golf ball-sized hailstone can reach terminal velocities of over 100 miles per hour. At that speed, yes, it's dangerous, very dangerous. But notice, it's still limited by terminal velocity. Without air resistance, that same hailstone falling from a thunderstorm cloud could be moving at over 500 miles per hour when it hit the ground. Air resistance saves us even from hail, just not quite as completely as it does from rain. There's something almost poetic about terminal velocity. It's the universe's way of saying that nothing can accelerate forever,
at least not while moving through a fluid like air or water. There's always a balance point, always a limit, where the forces equalize. It's a reminder that physics isn't just about things speeding up or slowing down in isolation. It's about interactions, about how objects talk to their environment, about how the world pushes back. And this principle doesn't just apply to things falling through air. It applies to anything moving through any fluid. A submarine sinking in the ocean, a snowflake drifting down from a winter cloud, even bacteria swimming through water. Each one reaches a terminal velocity based on its shape, size, weight, and the fluid it's moving through. The math is the same, just the numbers change. Let's do one more thought experiment. Imagine you're an astronaut standing on the moon. No atmosphere there. You drop a feather and a hammer from the same height at the same time. What happens? They hit the ground at exactly the same moment. Galileo would be proud. Without air resistance, all objects fall at the same rate regardless of their weight. Gravity accelerates them equally. But bring those same objects back to Earth, drop them here, and the hammer hits the ground first while the feather drifts lazily down. That's terminal velocity at work, making light, large surface area objects fall much more slowly than heavy, compact ones.
So the next time you're caught in a rainstorm, take a moment to appreciate what's really happening. Those drops have fallen from clouds thousands of feet above you, pulled by the invisible hand of gravity. But the air, that seemingly empty nothing all around you, has caught them, slowed them, brought them down gently. Each drop found its balance, its terminal velocity, and arrived at your skin, moving no faster than a bicycle, no harder than a tap. You're experiencing one of the fundamental laws of physics in the most intimate way possible, and you're completely safe because of it. And here's the real kicker. This isn't some obscure phenomenon that only matters in extreme situations. Terminal velocity shapes the world around you constantly. It determines how fast dust settles, how slowly pollen drifts, how quickly seeds disperse from trees. It's why fog hangs low, and why ash from a volcano can travel hundreds of miles on the wind before finally settling. It's why we can have parachutes, why birds can soar, why a piece of paper floats to the ground while a coin drops like a stone.
Physics is often taught as abstract equations and complex mathematics, and don't get me wrong, that stuff is important. But the real magic is when you see those equations playing out in the rain on your face, in the leaves tumbling from trees, in the gentle descent of a snowflake. That's when physics stops being something you study and becomes something you experience. Terminal velocity isn't just a concept, it's happening right now, all around you, keeping you safe, shaping the world, all thanks to air resistance. That quiet hero, pushing back against gravity just enough to make falling safe. So go ahead, next rainstorm you see, stand outside for a moment. Feel those drops. Each one is a tiny physics experiment concluding right on your skin. Each one fell as far as it possibly could, but arrived at just the right speed. Not too fast, not too slow. Perfect. And you'll know exactly why.